Okay. So let's start today by taking a look at the content from last week. So last week we introduced, in chapter 8, we introduced the notation A subscript N. This is the notation for sequence. So we're going to put the parentheses here. So this means the sequence. And the sequence going to have the pattern that they can be convergent or divergent if you take limit of an where n go to infinity and it's equal to L. L is a real number. This case you're gonna say that the sequence an is convergent. This is the case that mostly you're gonna see in the problem last week that we take limit and then you have so many ways to do the limit. So you have to get ready to do the factoring, get ready to do the using the conjugate. Sometimes you have to use a L'Hopital rule. This is the content that you can use any technique that you compute limit and then you get the L here. So remember last time we spent time on the L'Hopital rule here. So when you want to use the L'Hopital rule, it means that you face the limit that you in the form 0 over 0 or infinity over infinity. If you face the limit of the form 0 over 0 or infinity over infinity, you can just use the L'Hopital rule. Extend the domain first and then you apply the L'Hopital rule and then you make a conclusion back on the natural number. Sometimes you're gonna see the indeterminate form 0 raised to the 0, 1 to the infinity, or another one is maybe you're gonna see infinity to the 0 or something like that. So if you see something that looks complicated, 1 to the infinity to the 0 or 0 to the 0, something like that, you can just take logarithm and then once you take logarithm the power here gonna go down and then you can apply the L'Hopital rule. So this is the content that you should pay attention on because I feel like from last week some of you have a hard time to follow this one. Basically if you can compute limit and then you get the number L, so that means the sequence is convergent. So another case is if you take the limit an and this going to infinity or negative infinity, we're gonna call this thing the sequence is divergent. Okay. So there are gonna be two cases, convergent or divergent here. And this is the content we learned last week that we learned so many questions that how do you take limit and then you make a conclusion. Let's take a look at what we learned last time here. For example, this question, last time we learned that if we see n plus 1 over n to the n here, so you can see that when you take limit, it looks like it's gonna go to 1 to the infinity because n plus 1 over n here inside the parentheses here. If you take limit, it looks like you're gonna go to 1 and then the top part you go to infinity. What you learn here is you define a new function, the same function here with the same function here but change n to x and then you take log and then after that you take limit and then apply the L'Hopital rule. So they're gonna be one question something like this on the exam as well, so you should pay attention. And when you study for the exam one, so you should take a look at this type of question because it should be the one that it is a medium to hard level for you. But other than that, you just take limit and then compute the limit. For me, like sometimes you need factoring, sometimes you need conjugate, similar to what you learned in Cal 1. Okay, so let's take a look at the new content. Anyone have questions about the limit here? Later on, we're gonna learn series, so which is going to be different from sequence. So, but we're gonna learn sequence first for continue the sequence content first for today. Alright, so let's start by taking a look at, well, we're gonna spend about 10 to 15 minutes more on the terminology of sequence. So this is the another way to show that the sequence is convergent. So let's take a look at a lot of definition here. So the sequence is called increasing if an plus 1 greater than an. It is called non-decreasing is an plus 1 greater than or equal to an. By this I mean like everyone know what does it mean by increasing. So it match with our intuition. So increasing mean when you draw a graph y x here. So it's increasing mean the graph just keep going up. This means the function is the sequence is increasing. So non-decreasing it means it can be greater than or equal to the next term can be greater than or equal to the previous term. So it could be the case that but it can be the case that it just give you the same number on the next one, but it will never go down. So this is mean non-decreasing. So this is like the definition of increasing and non-decreasing. So similar to increasing and non-decreasing, you have decreasing and non-increasing. This is the same one but just different direction. When the sequence is either non-increasing or non-decreasing, we're gonna call it monotonic. And the last one is the bounded sequence. So when we say that the sequence is bounded, it means that there is a number m such that all the sequence, every term of the sequence an is in between negative m and m, which means absolute an less than m. So this is the same thing with the an always in between negative m and m. Why do we care about this terminology? Because if you know that the sequence is monotonic and bounded, you can conclude that the sequence is convergent. So in mathematics, we have some theory saying that, okay, if you know that the sequence is monotonic and bounded, we're gonna say that the sequence is convergent, which is on the next page. Okay, let's go to that theorem. It's gonna be here, but let's try to figure out example 4 first. I give you this 3 sequence. So can you tell me which one is bounded and which one is monotonic? So let's start by question A. So we have n square plus 1 here. So by this you can see that this one n square plus 1 is an equal to n square plus 1, right? And this means if you write a sequence, it's gonna be a1 gonna be 1 square plus 1, a2 gonna be 2 square plus 1, a3 gonna be 3 square plus 1, and gonna be 4 square plus 1, and so on. So it's gonna be 2, 5, 10, and then 17, and so on. So this is the pattern that you can see. It's going up all the time, like y, x, the first one is 2, and then 5, and then 10, and then 17. So the pattern just keep going here. So of course this is a subscript n, this is not bounded, because you can see from the graph that no way that this sequence gonna be bounded. So bounded means you're gonna have one number that's control the sequence, so it will never go beyond that line. But this is not bounded because it's gonna keep going up. You can see by the pattern that n square plus 1 is gonna go up. But an here is monotonic because it's keep going, right? It's keep going, so it's monotonic. So it just keep going up. So by looking at the formula, n square plus 1 is gonna go up here. All right, next one, b. So if you let bn to be 7 minus 1 over 2 to the n, so you can imagine that the b1 gonna be 7 minus 1 half, b2 gonna be 7 minus 1 over 4, b3 gonna be 7 minus 1 over 8, and b4 gonna be 7 minus 1 over 16. So it's look like if you draw a graph y x here, it's look like that you're gonna have the line 7 here. This is the line y equal to 7. This is the one that you start from 7 minus 1/2, which is like 6.5, and then 7 minus 1/4 is 6.75. So it look like the sequence that you have gonna start from 6.5 and it just keep going up. But now it just never touch 7, but it just get close to 7, right? Because the number here gonna just getting smaller, 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 and this number just get close to 7, but never touch 7, because at the end it's gonna be 7 minus 1 over something very big. So in this case, the sequence gonna be an is bounded. You know that it is bounded because it's bounded by 7. And an is monotonic as well because it keep going up. When you have the sequence that is bounded and monotonic, this means the sequence is convergent. Alright. This means the sequence is divergent because no way you can have the boundary of this one, so it's going to be the divergent. This is another way that you can make a conclusion about the sequence, but you know this is the easy one. You can take limit, that's fine as well. But imagine sometimes you see the function or you see the pattern that is very hard to take limit. You can make a you can use this theorem to make a conclusion. All right, the last one, C. So let's looking at this one. So we have cosine square n pi over 2. So n pi over 2 is something like that. You have to think a little bit. So when you plug in n equal to 1, so cosine pi over 2 is cosine 90 degrees, right? Cosine 90 degrees 0. And then when you plug in n equal to 2, so you're gonna get, well, I should get it slow. So cosine pi over 2 square. This is cosine, when you plug in n equal to 2, it's gonna be cosine pi square. And then when you plug in cosine 3 pi over 2 square, and then cosine 4 pi over 2, which is cosine 2 pi square. So when you have cosine pi over 2, so cosine 0 is 1, and then cosine pi over 2 is 0, cosine pi is negative 1, cosine 3 pi over 2 is 0, cosine 2 pi is 1. And then you square, 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 and then you can see that pattern gonna keep repeating the same thing. And it's keep going, the cycle is 4, and then you keep going. So which means the sequence gonna be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. So this sequence an is actually bounded because it's bounded by 1, right? So it's gonna be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, so it's bounded by 1. But it is not monotonic because it just keep going up and down, up and down, which means this sequence is divergent as well. So the sequence is gonna be divergent because you cannot find a good limit for this one, because sometimes it's go to 1, sometimes it's go to 0, and the pattern just keep going through the end of the infinity. So it's gonna be 0 and 1, 0 and 1, keep swapping. This is a good one to take a look at some theory. The theory that we have, if the sequence is bounded and monotonic, so if you have those two conditions, we're gonna conclude that an is convergent. Yeah, should be B. Or I can change this thing to an, so I don't have to fix a lot. That's right. Yeah. Well, like we always love to use an, right? Not bn and cn. So good. All right. So this is the theory that well, Are you good with this example? We are not going to touch a lot about this theorem, but I just tell you about this theorem that we have the bounded monotonic sequence theorem. So if you have a sequence that is bounded and the sequence that is monotonic, then the sequence is convergent. So this is the example that you can see that the sequences keep going up, but you know that it is bounded, so it's going to be bounded by something. And then this is a sequence that is decreasing or not increasing, and it is bounded by something, so it's gonna be convergent as well. So if you want to learn more theorem about this thing, you can just request to move to math department or something. So you're gonna learn. This is why this is how mathematics students, they learn something about the theorem, how to conclude the convergence, and then they have more complicated theorem to conclude that. But for you as an engineering student, you don't have to know it a lot. Sometimes you can use this type of theorem to conclude something super fun, something like when you buy a coffee and then you know that at one point the temperature of the coffee gonna cool down to one room temperature, something like that. This is the bounded monotonic sequence theorem, because when you buy a coffee, so the first time the time at t equal to 1 is super hot, and then it just cooling down, and then at infinity it's gonna go to the room temperature, so it's gonna be convergent as well by this theorem. All right. Before we move to the series, so we're gonna wrap up the sequence by taking a look at example 5. This is going to be true or false question. Should be in your exam, like for a short question. So let's see if you can do this type of question. If it is true, say it is true. If it is false, give me a counter example, or say why it is false. So part A, if limit an equal to 1, limit bn equal to 3, then limit an over bn equal to 1/3. It is true. This is by the theorem of the limit, right? So this is actually true. So this is actually by the limit theorem. Because when you see limit an over bn, so you can say this is actually limit an over limit bn, and then it's gonna be 1/3, because it's 1 over 3. Simple like that. Okay, so part B. If the limit an equal to 0 and limit bn equal to infinity, can you say that the limit of an times bn is equal to 0? Yeah, some people say no. So this is false. You cannot say it, because if you see 0 times infinity, this is the special form that it is called indeterminate form, or IF, which means it's gonna be sometimes that if you do 0 over 1 over infinity, this is equivalent to 0 over 0. Or if you do infinity over 1 over 0, it's gonna be infinity over infinity. You have to fix this limit by using the L'Hopital rule. So this is actually the indeterminate form. So you cannot, remember, you cannot say that 0 times infinity is 0. This is not true. So 0 times infinity can be anything you still do not know, because this is one type of indeterminate form. Because you don't know which one is stronger. Sometimes this part is stronger, sometimes this part is stronger. Sometimes it's cancel out in between, and then you get another number. So you have to fix this one, fix it by the L'Hopital rule. The L'Hopital's rule, which we already have example before, that when you see 0 times infinity, it's gonna be the one that you have to fix it with the L'Hopital rule. Good one. Next one. Is that good? Can we have? Okay, I will try to make it like here, like, so it will not go down much. Okay, so the next one, so example C, if the sequence an converge, then the sequence 0.00001 an converge as well. So this should be true, right? Because if you know that the sequence an is convergent, if you know that an converge, it means that you already know that the limit of an gonna be some number L. What about if you take the limit 0.0001 an? If you take its limit, should be the same, right? But you know, you can pull out the number, and then the limit here should be 0.00001 L. So it should be the same, like you can just pull out the constant and then you get its limit. So this should be the limit for the new sequence that you are looking for. So which means this is a true straight. This statement is true because should be good to do that, to conclude that the constant times an is convergent as well. So the last one, there is an example of a convergent sequence that is bounded but not monotonic. Do you know that there is a sequence that is convergent, bounded as well but not monotonic? Is there a sequence like that? Convergent, it must be convergent, bounded but not monotonic. Well, of course, if you are looking at the sequence that is not monotonic, maybe you are thinking of -1 to the n, because it's gonna just -1 1 -1 1. This is for sure gonna be not monotonic, right? If you want something that is bounded, maybe and convergent as well, maybe you just make something heavy on the bottom, like -1 over n to the n, and then this should be the first one gonna be, if you make it to be -1 over to the n over n, so the first one gonna be -1 over 1, the second one gonna be 1 over 2, right? Third one gonna be -1 over 3, and then -1 1 over 4, and keep going. You can see that the number is smaller. I mean the magnitude is smaller, but I mean the magnitude gonna go to 0 at the end, because the size gonna be getting smaller, but the sign gonna swap minus plus. So this sequence should work. This is a convergent sequence. This is a convergent sequence. Because if you take limit, it's gonna go to 0, right? The limit goes to 0. No matter what, it's gonna go up and down, the monotonic one. I think that should be the question that asks you to think critically. This statement is true or false on the exam one as well. But it's gonna be like, you know, one question, 1 point each one. So you just answer true or false easily. You know, sometimes good students, they have a mistake on the easy questions. All right. So any question on sequence? So before we move to the series. Series is gonna be like 2 times harder compared to sequence. All right. So let's try to learn more about series. If you don't have any question, let's talk about the series.มาถูกเวลามากเพราะว่าจะเริ่มซีรีส์พอดี Okay, so let's talk about series. So you already know what is the sequence. So the sequence is actually the function that has a domain as a natural number. So we already know, oh, when I say that this notation sequence, it's gonna be A1, A2, A3, A4, and so on. This is a sequence. Mostly we are interested in the convergent and divergent of the sequence here. But now we're gonna make something more interesting. This is called series. So now you add them up. So if you say A1 plus A2 plus A3, so basically you just use each term and then you add them up. This is called the infinite series. Let's try to do the observation here. So S1 equal to A1. So we're gonna call that the S, this is the partial sum. So S1 is equal to A1. S2 is gonna be you sum the first two terms of the sequence. S3 gonna be the first three terms of the sequence. Sn gonna be the first n term of the sequence. So if you want to know that the infinite series is convergent or divergent, one way that you can do is you can take a look at Sn and then you take limit of the Sn. If the limit of the Sn is equal to some number L, so you can conclude that the sequence is convergent. Otherwise, you conclude that it is divergent. So this is the basic way to do it. Does it make sense? Well, one more time. So when you see the notation of the sequence here, and the question can be like, okay, give me the answer. The series here is the series summation of AK here. Is this convergent or is this divergent? One way that you can do is you can trying to see the Sn. Sn, this is the partial sum of the sequence, and then you take limit of the partial sum. And if the limit goes to L, so you say it is convergent. If the limit does not exist or it is go to plus or minus infinity, you're gonna call it divergent. Alright, so once you see example, you're gonna get better with this content. But basically, we're gonna compute Sn, and then we're gonna trying to conclude that it is divergent or convergent. Okay. For example, if I see 1 over 2 to the k, everyone take a look at this. 1 over 2 to the k here, from k equal to 1 to infinity. If you expand only one term, 1/2, two terms, 1/2 plus 1 over 4, which is 3 over 4. Three terms, 1/2 plus 1 over 4 plus 1 over 8. This is 7 over 8. And then 1/2, 1 over 4, 1 over 8, and 1/16. So this is actually 15 over 16. Once you write them up, it's gonna be like group everything together. So it's gonna be 1/2, 3 over 4, 7 over 8, 15 over 16. So basically you start from 1/2 and then you're going to 3 over 4, you're going to 7 over 8, you're going to 15 over 16. It just keep going and that gets to number 1 at the end. So at the end we're gonna say that okay, this series is convergent and it's go to 1 because the limit of the partial sum is 1. Does it make sense? It's a little bit complicated that you have to find Sn first and then you take a look at Sn. We're gonna have so many tools to deal with it later, but this is the first way to do it. You can compute Sn and then you find the limit of the Sn. Okay. So let's take a look at the geometric sums and series. This is the first tool that we're gonna have for this class. So sometimes you see the sequence that it come with the a times r to the k minus 1. The sequence gonna be a, and then the next one gonna be ar, the next one gonna be ar squared, the next one gonna be ar cubed, and so on. So if you see the pattern like this, so you can use the geometric sum to help you to compute the limit of the series. So S1 gonna be a, S2 gonna be a plus ar, S3 gonna be a plus ar squared, and then when it comes to Sn, it's gonna be a plus ar squared, and then plus ar to the n minus 1. So I mean, from high school, some of you have seen before about the formula, how to deal with this thing. But if you don't know how to deal with this thing, let's take a step together here. So you can plug in the formula of the geometric sums here. So this is the formula of the geometric sum here. But let's follow the handout here. So we're gonna start by multiply r to the Sn. So you multiply r on this side, and then you multiply r on another side. So from this one, I just multiply r on both sides. And then after that, on the right hand side, I expand it. So I expanded everything. So I'm gonna get ar squared, ar cubed, and up to AR to the n. And then I call this thing the equation 1. I call this thing equation 2. And then if I do equation 2 subtract equation 1, or 1 subtract 2, doesn't matter. So you can see that the sum term gonna cancel out, because if you do AR and AR, they're gonna cancel. AR square and AR square, they're gonna cancel. AR cube and AR cube, they're gonna cancel. AR to the n minus 1, they're gonna cancel. So at the end, you're gonna have only A left. You're gonna have AR to the n left. And then on the left, you're gonna have Sn and Rsn. If you subtract these two equations together, and then you simplify, so maybe you're gonna do 2 minus 1. So you're gonna get Sn minus Sn equal to AR to the n minus A. And then you see this is the solution that you have by looking at these two equations. And then you simplify it, so you're gonna get Sn equal to A times R to the n minus 1 over R minus 1. Same formula as you learned in high school. But I mean, like some of you already memorized from the high school, so this is the next page. You're gonna have the formula here. So this is the formula for Sn. Okay, or this one. A times R to the n minus 1. I'll go back in a minute. Minus 1. So this is the same formula. You can just do this one or that one. The one that I highlight in yellow or the one that I highlight in here. So I'm gonna go back here for a little bit. Some of you. Can you see like 2 minus 1? So you get that one. This is how to prove the formula of the geometric sequence and series. Which means from now on, if you see the geometric series, you should be able to compute the value of the Sn. And then you're going to take the limit of Sn, and that will be the way that you conclude the convergence of the sequence sequence and series. Alright, so with this formula, everyone, so how do you conclude it? So you're gonna take limit of the one that I highlight in yellow. You look at the one that I highlight in yellow. So this is a formula for Sn. So now we're gonna take the limit. So what is the limit of the term that I highlight in yellow? So if r less than 1, what happened? So if r less than 1, so when you take limit of Sn, it's gonna be limit of this term. But because r less than 1, so r to the n gonna go to 0. And that means the answer gonna be A times 1 minus 0 over 1 minus R. So it's gonna be, the answer gonna be only A over 1 minus R. Same formula as you learned in high school. So the geometric series gonna be convergent when R, absolute R less than 1. And the limit is A over 1 minus R. This is the conclusion for the statement. So when you have the geometric series, if your absolute R less than 1, so this series gonna be convergent and its limit will be A over 1 minus R. If your absolute R bigger than 1, this is the case that the series gonna be divergent, because when you take a limit here, if R is getting big, I mean sometimes you can imagine, suppose R is equal to 5 million. So 5 million to the n, this is going to be super big, and the limit gonna be plus infinity or minus infinity, which means the limit does not exist, and that means the sequence, the series gonna be divergent. Same thing when r equal to 1 and r equal to negative 1, you're gonna have like a plus a plus a plus a keep going, and that's gonna be infinity, or you're gonna have a plus negative a plus negative a, and this is going to be the where you gonna be 0 or a all the time, because you're gonna have a and then you have negative a, and then it's gonna cancel out, so you get 0, and then the next one you add a, it's gonna be a again, and then you add negative a, it's gonna cancel out again, 0, so it's gonna swap between 0 and a, 0 and a. So basically when I equal to 1 and I equal to negative 1, they are all divergent. So to sum up for the geometric series, you're gonna have the only one case that is convergent, that is when r less than 1. This is the easiest series that you can have the geometric series. So to sum up, this is the summary of, we're gonna summarize this thing. So this is a summary of the geometric series. So when you have a is not equal to 0 and r is a real number, if absolute r less than 1, then the geometric series summation ar to the k equal to 0 to infinity, or the same thing with summation ar to the k minus 1, k start from 1 to infinity, it's gonna be a over 1 minus r. Basically, you can memorize that it's gonna be the first term over 1 minus the common ratio. This is the best way to memorize the geometric series. So sometimes the beginning point, the initial point can be different, can be k equal to 0, can be k equal to 1, but the best way to memorize this thing, you can memorize that it's gonna go to the limit, it's gonna be the first term over 1 minus common ratio, and you will never get wrong if you memorize that thing. So because the top part is always the first term that you need. So we have the example 6 coming up. So this is the practice that you're gonna learn how to compute the geometric series. Sounds good so far? How many of you have seen it before in high school? Geometric series? Yeah, I mean, if you learn in the Thai school, like, it should be in Matayom 5 or something. But for international school, maybe you're gonna learn it at some point in grade 11 or grade 12, it depends. So let's start by example 6 here. Summation of 1 over 2 to the k start from 1 to infinity. Here we go. So this is actually the geometric series. This is a geometric series where a subscript 1, so the a subscript 1 gonna be the first term gonna be 1/2, right? Because you can plug in k equal to 1, so this is the first term. Because they start from k equal to 1, you see that? This means start from k equal to 1. And the first term is 1/2. And then the second term, we don't care, because at the end, we're gonna just care the behavior of this one by taking a look at r. R is the common ratio. What is the common ratio here? So you can imagine that this form, it's gonna be 1 over 2 to the k. So it's mean when k increase, so you're gonna, it look like you multiply 1/2, 1/2, 1/2, 1/2, 1/2, right? So which mean r equal to 1/2. Does it make sense? And that mean because absolute r is absolute 1/2 is actually 1/2 less than 1. So you can conclude that the summation 1 over 2 to the k start from 1 to infinity converge. It is convergent for sure because absolute r less than 1. And its limit is a1, which is 1/2 over 1 minus common ratio 1/2 here. So it's actually 1/2 over 1/2, which is 1. So far so good? Anyone? So once you know that it is geometric series, you figure out your r, the common ratio. If the common ratio less than 1, absolute r less than 1, so the series is convergent and its limits gonna be the first term over 1 minus the common ratio. Does it make sense? This one mean if you add up 1/2, 1 over 4, 1 over 8, 1 over 16, and so on to the infinity, you're gonna get 1, right? You probably have heard about the Zeno paradox, something that you start from the point A and then you go to the point B. If the point A to be the you some people say that if you keep going half all the time, can you reach the point B there? So sometimes like you start from the point A, right? You go half and then you go another half and then go another half, you go another half, you go another half. It's mean like the first time you go 1/2, the second time you go 1/4, the third time you go 1/8, and then you keep going. At the end, you're gonna eventually hit to the point B, because 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot. At the end, you're gonna get 1, so it's gonna be 1 at the end. So you're gonna hit the point B. But you're gonna feel like, oh, we are not going to touch the point B because just keep cutting half. You can just take a look at, there are a lot of paradox here. You can just Google maybe you Google some time of the Zeno paradox or something, like lot of paradox here about this infinite series. The series is hard because it's plus to the infinity. So sometimes the pattern that you see is not matched with your instinct. This is the one that the famous one. Alright, so let's take a look at another geometric series. So suppose that you have part B, 2 times e to the negative k equal to 0 to infinity. Alright, this should be summation k equal to 0 to infinity. 2, and then e to the negative k, it's like 1 over e to the k, right? E is constant, so this is actually 1 over e to the k. Would you agree? And then this is actually the geometric series. Because you can see that the geometric series here, you have the common ratio r equal to 1 over e. And you have the first term a1. This is actually the first term. I love to say the first term, so it's easy for you. So the first term is mean you plug in k equal to 0. This is the first term. First term is k equal to 0. You plug in k equal to 0. That is the first term. So the first term is 2 times e to the minus 0. Again, e to the minus 0 is e to the 0, which is 1. So this is actually 2. Makes sense? And now, to figure out this is convergent or divergent, because your absolute r is 1 over e. Bigger or less than 1? Less than 1, right? Because this is, for those of you who don't know, this is actually about 1 over 2.7 something, which you don't care. It's e is about 2.7. Anyway, it's less than 1, which means it follows that the series, this is not a sequence, series to e to the negative k go to 0 to infinity. This is actually not that converge. Okay, and if you want to find its limit is, this should be the first term, which is 2, right? The top part gonna be the first term, the bottom part gonna be 1 minus the common ratio 1 over e, and that answer is 2e over e minus 1. If you don't know how to simplify, leave it there, so you still get full credit for my class. If you feel like Ajahn and we're gonna have a problem from simplifying this one, because if you simplify it wrong, you lose your point. This should be like a C question or D plus question, super easy one. Everyone in this room should be able to do this question. Like the geometric series is the easiest one. Taking a look at what you're gonna learn geometric series, and then the next one gonna be heteroscopic series, and the next one gonna be like, there's so many tests like P series, limit comparison test, integral test, divergent test. Like there gonna be so many series that you're gonna learn, but geometric series is the simple one. Okay, so
this one include in the test a lot.
I mean, this is going to be on the exam 1, so which is the part that you can collect the point, because one is come to the root test, ratio test, going to be a little bit harder. All right, so let's do part C here. Well, this is a little bit complicated, but still geometric series. Let's try to see, do you know what is a common ratio here? So you need to simplify first. Okay, let's do it. How to simplify it? So, okay, start from 0 to infinity. So, okay, I like the bottom part now, because this is 5 to the k. Should be good for me. But the top part, 2 to the 2k plus 1, this is actually 2 times 2 to the 2k. Everyone agree? This should be this. Because you can pull out that 2 to the 1 to be 2 first. And then that 2 to the 2k is actually 4 to the k. Agree? No. Okay. It's actually 2 to the 4 to the k. Okay, that's the first one. And then the next one, negative 1 to the k minus 1. It's negative 1 times negative 1 to the k. Is that okay? So this is negative 1. So negative 1 to the k minus 1, this is not easy to deal with. It is easy to deal with this one. Negative 1 to the k times negative 1. The first part is going to be 2 to the 2k times 2, and then that's the way I simplify it to 2 times 4 to the k. The reason why I do this, because I want to see k here. K to the k to the k, and then I will group it together. So this is going to be sum k to 0 to the infinity, negative 2. It comes from 2 and negative 1 here. Let's group it, negative 2. And then the remaining part going to be minus 4 over 5 to the k. Now, because I group 4, negative 1, and 5 together, and then power to the k. So this is actually geometric series with the common ratio r equal to negative 4 over 5. This is my common ratio r. And then the first term gonna be, well, we need the first term. The first term is, you plug in k equal to 0, it's mean negative 4 over 5 to the 0, that is actually 1. So it's actually negative 2. Okay, next. This is actually a convergent. The series is convergent because, okay, because BC, because absolute R is 4 over 5. Even R is negative 1, but when you take the absolute, so it's gonna be something less than 1 anyway. So good, this means the series is convergent, and its limit, it's actually the first term, negative 2 over 1 minus the common ratio, which is minus 4 over 5. Be careful about the bottom part here, because the limit here is the first term over 1 minus the common ratio. So this part that when you plug in, you need negative sign as well, not just 4 over 5, because actually r is negative 4 over 5. And then it's actually, on the bottom part, you have 1 plus 4 over 5. This is actually 9 over 5. And the answer gonna be negative 10 over 9. So basically, if you compute the summation of that one, it's gonna go to negative 10 over 9. This is called the geometric series. Of course, there's gonna be the case that r is bigger than 1 and that the series is divergent, but the convergent is more interesting because you can find limit. Okay? Okay, question on this one before we go to the next example. Okay, let's take a look at another geometric series. Example 7. How about 1.1.99, 1.99 square, 1.99 cube? This geometric series convergent or divergent? Example 7, part A. They didn't give you the formula, but you can see that every time you multiply 1.99, every time you multiply 1.99, basically this summation is summation 1 times 1.99 to the k, right? Make sense? 1 times 1.99 to the k. The first term is k equal to 0 to infinity. Because the first term, if you plug in k equal to 0, it is 1. The second term, you plug in k equal to 1, it's 1.99. The third term, you plug in k equal to 2, it's going to be 1.99 square. This is actually the form they want. So we got it. Now it is this one. So this is actually the geometric series. The common ratio r, it's going to be 1.99, bigger than 1, right? Which means this series is divergent. That's it. Divergent is series. Divergent geometric series is easy when it is divergent, because absolute r bigger than 1, you can conclude it is divergent. That's it. Okay, this example is so silly, easy one. 1 times e to 1 times e over pi to the k. Similar to the first one. Why is it so easy? K equal to 0 to infinity. And then this is also geometric series. And then I equal to e over infinity, e over pi. This is less than 1, right? Because this is about 2.7, pi is about 3.14. So this should be less than 1. So this means the sequence, the series converge, or it convergent. Its limit gonna be the first term over 1 minus common ratio. What is the first term here? So the first term gonna be 1. The common ratio gonna be e over pi. So it's actually pi over pi minus e. Okay. Still super easy. Yeah. So boring, geometric series. Let's try to do something harder. Slower. I was like, oh, I want to teach something hard. This is so easy and boring. Seriously, how many of you have seen it before, the series? None of you? Like only one? Oh my god, like...
อาจารย์ลินชัยแอนเกรสวิเคราะห์ขึ้นของแพทย์
Okay, I got it, because you grew up with the online classes. So it is possible, yeah, it is possible that they skip the content because of the online thing. Okay, so we have to be slower. Yeah, because when you learn it, it should be the first year that the COVID hit the world, so it's gonna be hard for the teacher in high school to teach you this thing. You're supposed to learn it in Mathayom 5 or 6 for sure. Alright, so one more question, the last one for geometric series. This is the challenge one, but I mean, once you know the technique, it's gonna be okay. So you know the decimal here, so you can use the geometric series to help you to express the number here as a fraction. So suppose that I have 1.7 0.035 and then repeat. This is the repeat one. So it means 1.035, 35, 35, 35, 35, 35, 35, and so on. So how do you write this number in terms of the fraction? So the technique is, if you have 1 point, let's look at this one. This is the one that interesting. 1.035. Repeat 3 and 5. This means 1.035, 35, 35, 35, 35, 35, and so on. So the technique is that if you wanna express this one as a fraction, what we're gonna do is we're gonna start from the first one is 1.035, and the second one is, this should be plus, is that right? And then 0.0000035. Well, we are trying to find a way that we're gonna do the series, but what I observed is maybe you're gonna do 2 at a time, like 35 and then 35. I'm just lazy to calculate the number. Let's take a look if I miss something. Hold on. Okay. Question. What is good question? Geometric series, right? 1 second. Okay, I should separate one as well, but this is 0.035 and then keep going. I'm trying to view this thing as the geometric series. So if you imagine this is 0.035, it is actually 35 times 0.01. Let's make it more easy by we're gonna just move number 1 out. It's gonna be this one. And can you see that this one is, oh, okay, one more 0. I missed one. Tube. This is why we love the scientific notation, because there are so many zeros. And then here, this should be the geometric series now, right, everyone? This already the geometric series. Just this part, the one that I use the parenthesis here, this is actually the geometric series. The first term gonna be 0.035, and the common ratio gonna be what? From this term to this term, it means you multiply 0.01. This term to this term, it means you multiply 0.01. Because each time when you start from this and you go to this, looks like you're gonna just move the the decimal here 2 units, right? So it means like you multiply with 1/100, and this go to this, you multiply with 1/100. So every time you multiply the common ratio 0.01. So that means the decimal that you use just shift by 2 because you multiply by 0.01 all the time. And this is the geometric series that absolute R is 0.01 less than 1. So basically this is a convergent series. So the answer gonna be 1 plus, so 1 come from the first one. I didn't change anything here, so I just keep 1 separate. And then the geometric series here gonna be the first term, which is 0.035 minus 1 over 0, 0, 1. Right, because the common ratio is 0.01. The first term is 0.035. And then now it's gonna be 1 plus 0.035 over 0.99. The same thing with 0.990. And that means 1 plus 35 over 990. It's this 205 over 198. I already did it beforehand, but this is the number that you're gonna get 1.03535. This is the number that you get 1.035353535 and so on. So any number that you have repeated decimal, you can do the same thing. If you write it as a geometric series, it's gonna go back to the fraction. You can hit the calculator 205 over 198, it's gonna go back to 1.0353535 and so on. Question on this one? Alright. See, when I do the recording, the battery just went down so fast. Like now it's 68%. I start from 100.
You use what form to record the video?
I record the video, the screenshot here. Like I record the screenshot here.
อาจารย์ use the one in iPad
Mm-hmm.
so there's no
Well, but I have to post the screenshot video to the YouTube or something later. That's.
แต่ปกติหน้าจอ
This is อัดหน้าจอ the same thing screenshot.
These days, Ajahn sound is a video.
มีถ้าเราใส่ไมโครโฟน open ไมโครโฟนมันก็มี
Ajahn
เปิดอยู่ครับ Alright, so any question on geometric series? Anyone? I do expect that everyone can do geometric series. Alright, we're gonna do 2 more examples and then the end of today. So the next example is called the telescopic series. How many of you did the mathematical Olympiad before or something like?
Maybe you.
No. So this is the one that people love to do it in, you know, right? The competition, the mathematical Olympiad competition or something. So telescopic series is like you have some term that cancel out a lot, and at the end you can compute the limit of the series by just taking the limit of the partial sum. So what you do here is you're trying to find a lot of terms that cancel out. So example 9 is going to be an example to show you that, hey, when you have something that you expand it and you can see that there are a lot of cancellation, so you can find the limit easily. Get ready. So I just want to do maybe 2 more pages and then we're gonna stop for today. So example 9. So let's start by looking at the following series. Summation start from k equal to 1 to infinity of 1 over 3 to the k minus 1 over 3 to k plus 1. Let's take a look. So first of all, if you take a look at S1, S1 gonna be the first term, only the first term. It's gonna be plug in k equal to 1. It's gonna be 1/3 minus 1/3 square. This is S1. Okay, you just plug in k equal to 1. S2 it's gonna be you sum the first 2 terms. It's gonna be 1/3 minus 1 over 3 square and then plus 1 over 3 square minus 1 over 3 cube. Right? S3 gonna be you add the first 3 terms. So it's gonna be this add this and then add this. Can you see the pattern here now? So when you compute S2, this the term in the middle gonna cancel out, right? When you compute S3, so the term in the middle gonna cancel out. Well, how? Because you can see that minus 1 over 9 here, plus 1 over 9 here, minus 1 over 27 here, plus 1 over 20, plus 1 over 27 here. It's gonna cancel, right?
Yes.
So cancel. So if you keep going, what is Sn? So Sn should be that term. Sn it's gonna be you add n term dot here. The n term at the n term it's gonna be 1 over 3 to the n minus 1 over 3 to the n plus 1. Would you agree? This is the Sn. And then you're gonna cancel so many terms here because 1 over 9 gonna cancel with 1 over 9 here. 1 over 27 here gonna cancel with something in dot here. 1 over 3 to the n actually gonna cancel with something in the dot here. So basically Sn gonna just have only 1/3 minus 1 over 3 to the n plus 1. This is Sn. And if you take limit of Sn here, it's gonna go to 1/3, right? Because you take limit of this one, this is constant. The limit of this term is 0, right? Because n go to infinity. This is gonna go big. 1 over something big gonna go to 0. So it's actually 1/3. So which means this series is convergent. Because the limit of the partial sum equal to 1/3. So this series is actually convergent. Okay, on the back row, 1 second, I'm gonna just move it up for you. Okay. The series is convergent here because limit of Sn equal to 1/3 and that is equal to a number. If the limit of Sn is infinity, so you say divergent. Does it make sense for telescopic series? So basically when you expand it, you're gonna see a lot of cancellation, and once you cancel everything, so you're gonna have Sn left, and then you take limit, and if the limit goes to any number, just one number, you say that the series is convergent. If the limit goes to plus or minus infinity, you're gonna say it is divergent. So I will not make it too hard for you because on the exam I'm gonna say that use telescopic series specified in the question, which means if you read the question and you see the word telescopic series or telescoping series, which means you can use this technique. Make sense? So let's try to do one more example before we left today. So before we leave today, so k equal to 1 to infinity, 1 over k times k plus 1. You can use partial fraction decomposition if you want. Here, 1 over k times k plus 1. This should be something k plus something k plus 1. What is going to be the question mark over there? Well, if you don't know it, if you can eyeball it, you can say, oh, Ajahn, I know what it is already. So if you know it, if you eyeball it already, you can see, oh, Ajahn, krab, if this is 1 and 1, so if you do the cross multiply, it's gonna be k plus 1 and then plus k, right, over k times k plus 1, right? Does it make sense? If I change this sign to minus, perfect, right? Because this is gonna cancel, boop, boop, and then it's gonna be 1 over k times k minus 1. But if you feel like, Ajahn, I cannot do this thing because this is way too fast, and you can do the slow way here. So let's say a over k plus b over k plus 1. And go back to the previous semester that I say that, oh, you can do k times k plus 1, and that is a times k plus 1 plus bk. This way for sure you're gonna solve for a and b. And then now you clear out the denominator, so you're gonna get 1 equal to a times k plus 1 plus bk. And this is true for all k. So now you set k equal to 0. Remember last time when we learned the partial fraction, we said x can be anything. So we just let x equal to 0, let x equal to 1. X can be any number you want. So this time you can let k to be any number you want. If you let k equal to 0, it's going to be 1 equal to a times 0 plus 1 and then plus b times 0. This is going to give you a equal to 1. And then if you set k equal to -1, I should pick -1 because it's going to make my life a little bit easier, because it's going to be a times -1 plus 1 and then b times -1. And this term going to give me b equal to -1. So now I can solve for a and b, which means this term actually 1 over k times k plus 1 gonna be the same thing as 1 over k minus 1 over k plus 1, because b is -1. Make sense? For those of you who feel like, Ajahn, I can eyeball it, you don't have to show me how to solve for a and b. But if you feel like, Ajahn, I cannot find a and b, so you have to set up something like this, so it's gonna be for sure you can solve for a and b. And then now you can see that it's gonna be the telescopic series, because if you take the summation, start from k equal to 1 to infinity, it means you take the summation k equal to 1 to infinity here. When you have 1 over k minus 1 over k minus 1, when you compute Sn, it's gonna be, the first term gonna be 1 minus 1 half, the second term gonna be 1 half minus 1/3, the third one gonna be 1/3 minus a quarter, and then keep going, and the last term gonna be 1 over n plus 1 over n plus 1, which mean not plus, sorry, minus 1 over n plus 1. And then now make a cancellation. So you can see that a lot of terms cancel out. So if you cancel 1/2, you can cancel 1/3, you can cancel a quarter, and keep going. So everything gonna cancel out perfectly. Shoop, 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 up to the end part. At the end, your Sn gonna only have 1 minus Sn here. Gonna be 1 over 1 minus n plus 1. And if you compute limit of Sn gonna be 1. Right, it's gonna be 1 because you take n go to infinity, so the limit gonna be 1, because it is 1 plus 0, this is actually 1, which means the series is convergent. Sounds good? Next time we're gonna take a look at the case that when the series is divergent. If you take limit of Sn and it's go to plus or minus infinity, the series is gonna be divergent. We're gonna take a look on at the divergent examples on Wednesday. But this is how we do the telescopic series or telescoping series. So basically they're gonna have some term that you can cancel out, and then you take the limit of Sn. Okay, I'm gonna stop at this page, and then on Wednesday we're gonna keep doing more and more and more examples. Okay, let me stop.